I think it's time to welcome on stage Dr. Graham McIntosh for the second keynote of our Transvalor simulation days, but the first presentation of the day. So Graham, we are extremely pleased to welcome you in this event, and once again, thank you very much, thank you very warmly for accepting to conduct this keynote. Graham McIntosh comes from the company Universal Stainless in the US, in Pennsylvania. You're serving as Vice President and Chief Technology Officer in this company. And as you mentioned in your in the abstract of this presentation, you have been one of the earlier user of the, let's say, former Forge 2D, which obviously is not market any longer. So. We are eager to listen to this keynote, and once again, thank you for being with us.
Well, thank you for the invitation, and thank you for the wonderful dinner last night. So after a brief overview of Universal Stainless, I'd like to give a fairly personal view of the past, present, and possible future of integrated simulation for cast and wrought products. Universal Stainless is based in the northeast of the USA. It's headquartered in Bridgeville, which is just south of Pittsburgh. We have plants in New York, Pennsylvania, and Ohio. Our main market is aerospace, but we also have other major markets where materials are critical. And in the bottom, you can see the range of the products we make. Largely semi-finished or finished products, ranging from ingot all the way through to bar, billet, wire, and shape products. Looking at the processes we have a range of melting activities from AOD, argon oxygen decarburization, 50-ton melts, through to 12-ton vacuum induction melts. Much of our material is then remelted through a vacuum arc reduction remelt process or electroslag remelt process. And then we have a variety of hot working options. Our Ohio plant has the first radial forge in America. It's a brand new facility, 2011, with state-of-the-art equipment. So looking at the past of my modeling experience, it goes back to even before Forge 2, when our company at that point had an R&D group in the States, in Houston, which carried out simulations with a code known as CALPHAD. This is a precursor code to what is now known as Deform, so a pre-commercial version of it. And my company was involved in a collaboration to develop that. Moved on to purchasing Forge 2 and working very closely with Transvalor. Then I changed companies and moved to the States in 2001, where we started looking at codes for ring rolling development. And at that point, there was a manufacturing technology program sponsored by the US government, which was a 2.5D non-thermally coupled approach. And that was created that way because of perceived constraints on the capabilities of code and what could be developed. That funding was lost in 9/11. And I started working with Transvalor again, and we developed a very successful implementation, I think the first industrial ring rolling code in the world. 2008, I moved on to another company which already had a variety of codes, both Forge 3, Forge 2, Deform. So a lot of code availability, but including melting codes, which was my first introduction to them. So in 2008, I moved to Universal Stainless, and we have nothing. But I'm there to help grow this company, and I'm aware of the importance of modeling. And what I'm looking at is developing a strategy for implementing an integrated process chain for all our products and for all our processes. A very quick focus on the very early days of modeling back in the late 80s. So CALPHAD I've already mentioned we were using. Those simulations would take weeks, and to get a design iteration would take months. So very, very unique activities were used there, very painful. Very specialized expertise in those days. There was no automatic remeshing, so the whole skill base was quite different. State of the art back in the late 80s was physical simulation, plasticine. It was quick, metallurgists could use it, we could make dies and modifications very easily. So when I was given modeling as a project in my first job, I basically stood up and said, that's not the future of where modeling needs to be, it needs to be digital. And it's very expensive and it's very slow, but it will improve. The other big change I made was for a European company, but really a US company in Europe, in Scotland, was not to take the American solution. And the reason I did that was because of adaptive remeshing, which has been implemented. So that was an innovative game changer. And the CALPHAD development was saying it cannot be done. I said it can be done, it's happening in Europe. So we did that approach. And the point I'd like to make here is in a few years, we transformed design of forging manufacture. And the big thing was the increase in computational speed, partly from the adaptive remeshing, also improvements in efficiencies and improvements in the computational power. Simulations, which once took weeks, then took days. When it got to the point of taking hours, it could be integrated into the design cycle. And industry waits for no one. So if it can't be integrated into normal processes, it becomes a special case. When it's integrated, it becomes part of the normal solution. And that absolutely transformed how we did design back in the early 90s. Staying on the present, I could argue that engineering materials is very easy. We've been doing it for a long time. I can argue that we can do process development very easily. And a lot of tools are being developed to do both of these things. It's very exciting things for materials design happening just now from ICME. But I argue that effectively simulating manufacturing processes is really difficult. Too many boundary conditions, too many assumptions, too many unknowns. And as we've heard already this week, computational power remains an issue. So we make approximations. Our perspective I'd like to emphasize here is we can design all we want for good materials, but it's when a material fails that's important. And if we're not designing for the failure mode, for the defects, we're not doing ourselves a service for this industry. So an example of that would be a coarse grain, excuse me. Coarse grain and a fine grain matrix, or particles in a matrix. They come from the melting process. They come from solid state reactions after the melting process. So what happens upstream in the process is extremely important for the failure mode downstream. And I think to model that, to simulate that, we have to do the individual process, but we have to do the process chains from beginning to end, because the output of one process is the input to the next. Otherwise, we're back to making assumptions and approximations. So with regard to where we are, I'm doing a technology landscape for my company as to where we want to go, and looking at what's available. And for solidification modeling, there's some very stable codes out there, very mature. But for remelting, for the vacuum arc remelting, electroslag remelting, it's very immature. There's not much out there. And it's essentially almost all 2D, and certainly the commercial solutions appear to be 2D. A lot of approximations come along with that. Thermo-homogenization is very important as an industrial step, where we reduce the microsegregation from a cast ingot prior to hot working it. And I think that tends not to be looked at in terms of a modeling technique. I think the tools are available, but not many people are necessarily doing it. And then obviously hot working heat treatment is extremely mature over the years. So focusing on remelting and remelting simulations, 2D commercial solutions are available, but they're extremely limited, I would suggest. They don't mimic the real nature of the environment, which is a very, very aggressive dynamic environment, melting metal. So the challenges for 3D is understanding what's going on in that dynamic environment, and also computational limitations. 3D is a problem for many of us. Any solution has to look at the transient states at the beginning and end of the process, as well as the steady states in the middle. So there has been a lot of progressive developments over the years. As you've seen from my career, I've been in and out of modeling in various areas, but not really looking at remelting for some time. But I'm beginning to look at that again. And it's encouraging to see that there's been ongoing development. Looking at what's happening just now in support of that, there's a very interesting current development in the States, which is looking at how the melt pool behaves under the dynamic arc. This is courtesy of a company called Ampere Scientific that we're engaging with. And what's happening there is using an external magnetic field to understand what's happening with the arc. And the images on the right show the position of the arc as it varies So if we don't know what's happening, we don't know what's happening on the local solidification that gives the local microstructure that ultimately gives us the final properties that we're looking for and the defects. So by being able to measure something, we can then analyze it, we can then improve it. And I think that technology will help us understand how to develop and correlate and validate remelting codes. So this I see as a game-changing technology, which is just emerging. Very briefly, does anyone apart from myself really care about remelting? It's encouraging to hear some focus on it in the presentations this week. But 20% of the specialty steel market by dollar value is in remelted products. The work that's been done over the years, and I did some early work in the late 90s trying to integrate across the supply chain, shows there's a level of importance. So this is important to the industry. We don't have it because it's a difficult challenge. So looking at the integration factor, it's very inefficient for industry to have multiple codes, multiple potential hardware solutions, multiple licenses, multiple training programs. What we'd really like is one solution. And I think I've mentioned trying to focus that remelting is a major weakness here from a process itself. But in terms of integration, getting data transfer between multiple codes, I think it's different as losses of efficiency. And moving from 2D to 3D to 2D brings a lot of inefficiency. So it's not really what industry is looking for. And if we want to get to the level of fidelity that will give us defect prediction, we've got to go beyond that. It is encouraging that there's a number of activities where completely independent code providers are providing some level of integration. And looking at what's happening with JMAT Pro and Transvalor and other codes, there's a lot of integration going on. So I think things are coming to a point where we can contemplate getting a single solution if we have one company which can develop for all the processes. But today that does not exist. So for the future, computational issues, we've heard them in the presentations yesterday, we all face them. For me, they lead to a lot of approximations that just limit the value of a simulation. They're also very expensive. And there's approaches that can be used with academia, there's approaches that can be used with industry, and industry typically is not going to have the very expensive approaches for hardware. So supercomputers, to use that term, may be put into national labs and maybe put into large universities, but it's very unlikely that industry will have access to that sort of technology, at least for the foreseeable future. So I wonder whether advances in computing that really have no background in will come, such as quantum computing. Is that really a game changer, or is it irrelevant to us? But we should be looking at whether that is something to plan into our design cycles going forward. CP evolution will be changing as we move away from silicon architectures. For the shorter term, perhaps cloud-based solutions are useful for industry, where large computations can be done off-site. I think an interesting direction is open source. There's some literature out there showing that computational efficiencies can be made with a different code approach. So it's nothing I'm particularly involved in, but I can see the evidence in the literature. So I think we need to keep an open eye in terms of what approaches can be taken to improve the computational limitations to make useful codes for industry. And that perhaps takes us to simulation service, simulation service providers, because industry may have a useful set of tools and techniques for certain applications, but for a fully integrated supply chain, which is 3D, it may need to come outside of that, back to the code, the cloud solution. So, going over again, there are very, very large challenges in the industry to get what we need today. We've been working at it quite a long time, sometimes in close collaboration with the code writers, and I think that's very, very important. We've had some discussions this week about validation. That should start at the beginning of the code development, not afterwards, and go through a redesign loop. So collaborations with industry, academia, labs, code providers are all very useful. There's a limited integration across process codes today. Again, it's getting encouraging to see more and more happening. But what industry I think would love to have is one provider. And Transvalor, I can argue, is the most likely solution for that with the suite of codes it has today. If that doesn't happen, there will be individual code providers emerging and are emerging, and leading to a more inefficient implementation of what we really want to do. And inefficiency is not only expensive, it leads to inaccuracies. I think incorporation, identification of game-changing innovations is important. It's very easy within any organization to look at what can be developed in-house. Transvalor has an excellent reputation, and I would argue the best in the world for working with other partners. But perhaps a European focus, so make sure there's a look at what's happening elsewhere around the world. This is an international simulation days, so you have an international perspective. But keep an eye on game-changing innovations that can be used to help develop codes more effectively, more quickly. So if I look at where we are in 2017, state of the art, we're a small company. I'm looking at what we want to buy, what processes we want to simulate, how we want to go forward. There's no real one good solution I see. So maybe I wait for another 30 years. Maybe we start working on it. But it is very interesting to see a number of the evolutions, the developments in the last few years. But I have to say, having gone through my personal background there, this feels a lot like the late 80s. Codes are emerging. They're not necessarily mature. They are in some cases, but not in every case. 3D computation. Back then, it was 2D computation was very, very slow. That's not a problem. Now 3D is very slow. And it limits what we work on. We make approximations. We say it's too difficult. We use all sorts of limitations that mean the defects that we want to predict and understand for the processes. We can't get there with those approximations. It's very difficult. So what's the point of doing it? So I think there's lots of opportunities available here to mature, transform the industry all over again. I can tell you, having lived through it back in the days when engineering was done on a board, not a computer, that it was transformational. It completely changed the industry. That has not happened for integrated process chain simulation. And I think it needs to happen, and I think it can happen. So my question is that a challenge that's of interest? Will it be taken up? If, when? Mañana? Tomorrow? Next year? 30 years? Or can we start today? And very encouraging to see some of the presentations this week. That journey has begun, but I think it needs to accelerate. And what can be done to accelerate it? And industrial collaboration, I think, is necessary to do that. And I can stand here as a representative of Universal Stainless and say, we're trying to move into that area. We don't have a lot of background, but we have a lot of skills, equipment. And so we're interested in working on collaborations and code development. And I know it doesn't happen tomorrow, but if we don't start, then it's not going to happen. So that's really all I was interested in getting across to you. If there's any questions, I'll be pleased to take them.
I will make some comments because we need to react a little bit after that. What I like first of all is this idea of game changer. Okay, I think that we in Transvalor we try to every time to be on that side. You mentioned remeshing. We could have said or also make some comments when we move to parallel computing, when we introduce optimization and so on and so on. What's going to be our next development, which could be seen as a game changer? Maybe, as you mentioned, the VAR and ESR. This is something that you have seen working on, and hopefully we will manage to provide something which is matching the industrial expectation for sure. The other point that I'd like is and this is where I believe we do have some strength is in terms of interoperability between the software. You're saying that you're looking for something like a global solution. Do you believe that basically what we can do on the casting side with Thercast and what we're doing on the forging side with Forge, this is a good strength, this is important for a company like you guys?
I think it's very important. The weakness, like I say, is the black hole of not having a remelt. Because the remelted product is a more critical material. It's a higher margin material. So it's going to drive the value more. So that's what's happening in the Thercast and Ford is setting the scene for what needs to be done. It's got its own applications for sure. But in terms of the valuable materials, it's missing a whole segment there. And there's uniqueness on the remelting side. It's why it doesn't exist today. So, or doesn't exist well today. So I think that slot needs to be filled, and then there's a complete chain. And at that point, as we say in the States, it's a slam dunk. That's what we're looking for.
And maybe one last question, which, because I'm not enough specialist or not yet on that topic. When you talk about remelting, is it something which is applicable essentially for steels, or is it something that we can expand to other kind of alloys?
So absolutely expands to other alloys. It's used to clean up the material, make it more homogeneous, get rid of nasty elements, nasty precipitates. So you'll find it in the more expensive materials. The most advanced work that's been done today is on titanium. Okay. So titanium, zirconium, nickel-based superalloys. Some of the work I was getting involved in back in the 90s, it still continues today. There's some references there. It's nickel-based superalloys. Aerospace has driven a lot of the development. Nickel-based has driven a lot of the development. So Universal Stainless is not a steel company. That's its roots. We do melt, nickel-based. We do hot work, titanium. So I think that specialty area is what will drive it. And aerospace makers may still continue to drive it. There's follow-ons to the Mantech initiatives today in the States, looking at doing things here. But it feels like the past. So what's been done is looking at 2D approaches because that's all that's been offered. Okay. And that's fundamentally limiting for the nature of the process. And so we can do stuff. It's always good to do stuff. If you don't do anything, you won't get anywhere. But I think it's very, very limited. And what has been done is exciting. But in 30 years' time, that's not what we'll be doing. So I'd like to again say, are we going to be waiting 30 years? Or are we going to do this a little bit sooner?